Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Mentor, a Siemens Business, with Moses Satyasekaran, who's going to talk today about ContextAware Debug. Moses, debug is getting much more complicated as chips get more complicated. What do we do about it?
So we've been, as EDA software providers, we talk to customers about debug and verification. And what we hear from them on a constant basis is debug is where they spend most of their time. So it's around 50% of their time is spent on debug. So what we are looking at is why are they spending so much time and how can we make that process efficient? And what we are finding out by double clicking on that problem is the chips are getting more heterogeneous. What I mean by heterogeneous is it's no longer about just performance. Performance is key, performance is table stakes, but it's more than performance. It's about software debug, it's about power debug, it's power integration, it's clocking, reset. It's just all these things are increasing the complexity of debug, and that's why users are spending a lot of time trying to debug their chips at this time.
Even when they do the debug, are they confident that they've got everything closed out and the right answer on everything?
There are mechanisms, there are metrics that they're tracking. Users like coverage metric, there's static metrics that helps close them, but users have some metrics, they're getting there, but it's not fully sewn up at this point. Yes, that's what we hear from users.
So why don't you draw this out for us?
Sure, I'll do that.
Moses, what are we looking at here?
What we are looking at here is a snapshot of what users are dealing with. Let's look at this, right? This is a design underscore test. We all understand this. This is the chip that you're trying to make. What this used to be was small. Now it's massive. Some of our users are saying the simulation's running weeks. So here's where we're talking about importance of performance and capacity. So this is critical, and I talked about how this is table stakes. I'll talk about how we can some of these things are getting addressed at this time. Then you have test bench. So industry has consolidated with standard UVM. So you have UVM test benches. UVM is a large software project by itself. Everybody understands that. It's a lot of object-oriented programming. It sometimes is so massive. They are bigger than design under test itself. So there's UVM debug that needs to be considered.
Big chips also have a lot of dependencies. They have a lot of clock domains. They even have a lot of power domains. All this stuff is setting in motion things like it's on, it's off, it's not quite on.
Yeah.
Well, how does that affect what you're debugging?
Yeah. So if you look at this design this size, there are clocks and reset domains, and designers are grappling with this, right? So they have multiple clock domains, multiple reset domains, and to add to this, you have power aware. There's power intent that's coming up from UPF. So you have a code that has clocking, resets, and then you have another dimension coming in where you have power intent that's getting locked into your design under test. So all these things have to be considered. Now, these are some of the things that you might have already known about. As we are going towards automotive and other Internet of Things, there's safety, functional safety, ISO 26262 requirements. All those things are coming in as well. So there are other requirements like functional safety. You have all your DUT of this size will have processors in them.
As you get into the automotive world, you're dealing with potentially use cases as well, right? So your ambient temperatures may be different from one to the next. Now you have to do the context aware that goes well beyond what you were testing for in the past.
Exactly. So well beyond not only that, and we're also looking at mixed signal domain. So because there's a lot of analog components that come in as well. So there's mixed signal domain, there's functional safety domain, and then on top of all these things, the chips are getting so massive. You have emulators and software validation that you have to bring up software and software validation using prototyping systems. So those are the things that are making your system more complex and heterogeneous.
So as this gets more complicated, obviously it's taking more time. What's the solution to knocking down that time?
Yeah, let me show you what the solutions are.
So what can be done about this?
Okay, let's talk about performance first. So we talked about performance being the table stake, right? So when we discussed this initially, I talked about how we want to, when we look at performance, we want to look at not only debug performance, but also the engine performance. One of the things that you want to look for is how can we alleviate pressure from the engine so it doesn't have to dump so much data. So that's what we're looking at from Mentor ContextAware Debug platform. So what we're doing here is we're doing this thing called reconstruction. So what this means is when user dumps data from the engine, whether it's simulator, emulator, or prototyping, we dump only the data that what we call our primary nodes. Everything else is reconstructed. So your data is available, however, your database is not bloated. So you have a smaller, compact database. There's less pressure on the engine. It doesn't have to churn out so much data, so your engine runs faster. And you don't have to think about what data should I record, because all data is available on demand and it's instantaneous.
You've got a lot of data there, though, right? I mean, your capacity has got to be huge for this.
Mm-hmm. Yes. So this is two-pronged approach, right? One, for the capacity, you want to have a modern database. We invested a lot on the modern database, but we're also looking at the technology from how do we reconstruct. And here's where the ContextAware kicks in. So for an engine like simulator, you can adjust the reconstruction to what the simulator engine needs. But for a prototyping system where FPGA data cannot be moved as much as you want or as much as you would like to get, you need much higher reconstruction. So based on what engine you are targeting, the ContextAware Debug platform from Mentor will adjust the reconstruction so the data is available and it understands what the engine needs are, what the engine capacities are, and makes the data available for you. So this makes your debug process much more, you don't have to think about what data you're recording. You don't have to think, okay, do I have to record this data? Do I have to keep this data? Do I have to throw the switch in? Or what should I do, right? So those aspects of it are removed, what we call the trivial aspect of debug. So you are working on value add. So you are looking at, okay, where does the problem come from? So that's basically, from performance standpoint, what we are providing.
So basically what you're trying to do is reconstruct things on a much broader basis where you pull in lots of different factors, right?
Yes, absolutely, yes, that's what we're trying to do. And that's not stopped with just the design under test. We're also doing a lot more on the UVM debug standpoint. So like I said, it's a large software project. I don't want to scare anybody, but it is, UVM is where you invest once and then it's reuse. There's a lot of reuse that you can do with UVM test bench. So as users are investing in it or are already invested in it, what we hear from our customers is they are inheriting some UVM test benches.
Is it the same skills that people have been using, or they now have to think in a different dimension?
They have to think in a different dimension because initially it used to be all RTL, right? It's just clocking and all those things. Now it's a giant software project. It's object-oriented programming. A lot of our hardware engineers are not trained to write software, but they do know how to look at a waveform, how to debug, how to look at a schematic, how all these things fit together. So what we are doing is basically building up UVM right into the debugger. So UVM is a first-class citizen in the debugger.
When did you first start seeing this? Was it just at certain process nodes such as the FinFET generation? Was it as new chips started coming into the market around things like AI and more heterogeneity, new markets, 5G, or did it exist all the time and it just that people didn't have to pay as much attention?
So it existed all the time. right? People weren't paying that much attention because the complexity wasn't that much, right? Now, with the amount of requirements that you have for especially IoT markets, where there's functional safety, where there's also the automotive market, where there's a lot of analog components are coming in. So now we are looking at this problem in a multi-dimensional way, which you could still deal with what you have today, but that's with the current resources that you have, current product timelines you have, you need a context-aware debug where you can move on faster.
And this isn't just ASICs too, right? This can also be FPGAs, DSPs, and anything else.
Oh, absolutely. So FPGAs, the days of whole burn and churn are gone. You cannot go to you cannot go to the lab and figure out anymore because FPGAs are getting complex as well. FPGAs are addressing wide range of markets that need some of these advanced debug technologies so that users can run verification in advance and closed loop. All FPGAs now have an ARM Cortex in them. So you have a hardware-software debug in there. So there's a lot of this heterogeneity that are baked into FPGAs as well that needs sound verification, advanced debug, so that you're spending less time in lab, taping out products faster, and everything works after that. Yeah.
One of the tools that everybody's been using for debug as well as verification is UVM. How does that fit into this?
Okay. So UVM is the test bench methodology that industry has standardized in, and for good reason, because you have massive chips that you cannot keep writing new test benches every time. So this is a reuse methodology, and also from the financial standpoint, UVM is where you can find a lot of engineers, right? So, however, there are hardware engineers that are trained in hardware, like VLSI and all those things, that are still writing UVM, and they need to write UVM because they are taping out advanced chips. And what happens to them is they want to look at debug in a certain way. So what we are working on and what we are doing right now is making UVM as a first-class citizen in our debugger. What that means is now you can look at your object-oriented classes in waveforms. You can view your UVM structure in a schematic. So the visualization is now context-aware. You're going from RTL to a software block, but you're still able to see the same UVM block in context of the dot in the same viewing mechanism that you're used to. So you're not spending time trying to learn something new, or even if you're trying to spend time learning something new, you just got some of the basics down pretty quickly.
You're also breaking down some of the silos that have existed in the verification world, right?
Yes. Yes. Speaking of silos, we have now the power intent. I make my decisions on buying a cell phone based on how long the battery has. Of course, battery lasts. So of course, it's the same with whatever you buy. You're looking at how long this IoT object or IoT device is going to hold power. So power becomes critical, whether you are designing a massive processor, there's a couple power domains, or if you're designing a small IoT device, but it has multiple power domains turning on and off. So the interesting thing about power is it's not baked into the design under test. It's the power intent is coming in from UPF. So UPF is passing on the power intent into the design under test, the RTL. So when verification engineers bring up their debug, now they've debugged their functionality, you turn on UPF. What happens, right? You don't want to go to a different context. What you need is a place where, whether it's schematic, whether it's waveform, where most of our engineers spend time on, or whether it's your source code, you should be able to turn on power intent and say, okay, what happened to my isolator cells? What happened to my level shifters? Due to the power intent, how did that change my simulation? How did I change my emulation output,
So basically what you're doing is creating the equivalent of a stack for verification, right?
That's right. So absolutely. So we are building the stack where you're sitting in the single cockpit, and you don't have to really think about, oh, is this now do I have to do power, or do I have to go open another software? So we're just breaking down the barriers, and we're also trying to bring in a single communication language between design engineers, power intent engineers, and verification engineers. So it's just everybody can speak the same language through debug.
What about regressions, which are a key piece of this?
Okay, so debugger is critical, but now regression debug, right, is also getting important, right? So we are spending a lot of time putting intelligence in regression debug from Mentor solution standpoint. So what we are looking at, and we will talk about it more in the later videos, is we are building where regression has a lot more deep learning capabilities. So what we could say is, based on what you've done so far, we could predict when your project completion is going to happen, because we know how much simulation, emulation, prototyping you've run, what your coverage looks like, what your static tool data looks like. So we can look at all these things and say, well, you are this much closer to closing in on. Or you have a bad check-in. We can actually go back and say, okay, this is a bad check-in. We are going to back out the check-in. We're going to call the debugger and basically pull in the data for you. So the idea is simplifying the trivial stuff, whether it's at the point tool level, so you're breaking the barriers, or whether it's in a regression level where you're dealing with space and time across multiple sites. So that's what we're working.
Moses, Satyasekaran, thanks for a great explanation.
Thank you, Ed.